Yo, welcome back. We are going to do a short little question on seeing the limit numerically. So, evaluating limits numerically is a solid way to do a limit if all else fails, but it has its drawbacks. Typically, in pre calculus classes, you spend a lot of time doing this. We're not going to spend too much time on this, but I will show you an example. So, let's consider the popular calculus function f of x equals sine x over x. And this is the limit I want to do here, the limit of sine x over x as x goes to 0 from both sides. In order to do this limit, we're going to go ahead and get some help from Desmos, which could seem a little weird because I said let's do it numerically, and we're going to do it actually graphically first just to tie everything together. So if I graph the function here, I get this, which is not very revealing. So I'm going to go ahead and I'm going to change my window. I want to see further to the left, so I'll say negative 25. Further to the right, I'll go to 25. And since this is squished a little bit, maybe I'll shrink my Y scale as well and just kind of go above 1 and a little below negative 1 to see what's going on. So this is a little bit better, a picture of what's going on here. So you have this sine graph, manipulation of a sine graph that has these waves, and as you go to the right or the left forever, the waves actually get tighter and tighter and tighter. Those amplitudes shrink, so to speak. It's almost like it's wrapping around the axis, right? You can kind of see that if I look to the right. So that's the graph. So now a couple things. There's an issue with this graph. It's not graphed correctly. Like, what the heck do you mean? If I was to kind of click anywhere on this graph, I can just take a point. So like, for example, this point here, 1.88 comma 0.5067, that's a point on this graph. Well, if I go over here and click on that point, I see all of a sudden a hole pops up and it says 0 comma undefined, which really means that that's not a point on the graph. There's a hole there, and for whatever reason, I'm not going to get into the computer science behind it, but it's not graphed. They don't graph that hole for us. So it's kind of an incorrect graph. They should graph it, but they don't graph it. Again, what the heck do I mean? Well, if you input 0 into this function, you kind of know there should be a hole there because you'd get sine of 0, which is 0, but more importantly, divided by 0, and 0 over 0, that's not defined. And even if I had Desmos evaluate f of 0 for me, so I said, hey, Desmos, go ahead and plug 0 in as an input, tell me what the output is, and it says, hey, it's undefined. So there's a little bit of a workaround here. I can actually plot the point 0, 1, which is not exactly how I want to do this, right? So if I plot that point and then change the color and make it a hole, now I get what the graph should look like. Okay. So now, if you remember, the original question here was what's the limit of f of x as x goes to 0 from both sides? Well, let's do it graphically. Let's pretend like we have this graph in front of us, which we do, so we don't have to pretend, and see what the limit would be. So as my x values go to 0 from the right, what are my corresponding functional values go to? So see, as I'm tracing along here, my x values are getting smaller and smaller and smaller, right? They're getting closer to 0. And what does it look like those y values are getting close to? That's like 0.983, get a little closer, 0.9904. Hopefully you say 1, okay? Now let me do it this way. As x goes to 0 from the left, right? So I can kind of trace. It's like my little limit buggy as he's crawling along the curve. What is he getting close to as I get close to 0 from the left? And again, you can look at those y values. It's getting close to 1. So this limit is in fact 1. But we just did it graphically with the aid of Desmos. Well, what if I didn't have a graphing calculator that I can use and I wanted to do this limit numerically? When we say do a limit numerically, we actually kind of mean make a table. So the cool thing is that Desmos will do this for us. So I'm going to go ahead and make a table, and I don't want these little subscripts here. So I just want this to say x, and I don't want this to say y. I actually want it to say f of x, which means it's going to use the function that I have here, right? So for example, if I was to plug 0 in here, you see it says undefined because there is no functional value at 0. So now how would I use a table to do a limit? And it's not going to let me scroll down, so I'm going to kind of do this. What I'm going to do here is I want to put 0 in the middle of my table, and then I kind of want to pick values that get closer to 0. So like, I don't know, for example, maybe I'm going to take a value to the right of 0, not exactly at 0. Maybe I say something like 1. You can see there's the point, there's 1. But now I want to pick values that are going to get closer and closer to 0 from the right side. So maybe I do 0.5, right? Maybe I want to get closer to 0. Maybe I do 0.25. Maybe get even closer, do 0.1. So this now is a graph that's showing me what the outputs are as I'm getting closer and closer to 0. Now remember, if I put 0 in, I get undefined, okay? So now this would be a numerical thing. You'd be able to crunch these numbers for any particular function. You might need a little bit more help than other, depending on what function you use, but you can crunch some numbers and you can observe, what does it look like these y values are getting close to, right? And the closer you get, hey, maybe you want to get closer. Maybe you want to do 0.01. Maybe you want to do 0.001, right? And you can see it looks like we're getting closer and closer to 1 as our x values get close to 0 from that right side. Now I put 0 in the middle of the table. Let me go and check out what's going on the left side. So, I can kind of do the mirror image if I want. So maybe the last value I did was negative 0.001. That's just on the other side. All right. And then we have, let's see here, negative 0.25. And all I'm doing is mirror imaging, right? I'm just flipping negative 0.5. And then it's weird because I'm doing it kind of in a reverse order, right? So maybe I start at negative 1. Then I go to the x of negative 0.5, there's the y value, x of negative 2.25, there's the y value, and so on and so forth. And you can see now as I'm getting closer to 0 from the left side, I'm kind of like going up here the way I did it, right? I see that the limit looks like it's going to 1. Okay, and that's how we can do a limit numerically. So if you want to do the limit as x goes to some value, it's not always going to be 0, guys. Whatever that value is, just take that value, put it smack dab in the middle of a table, and then pick values that get closer to that value from one side, the positive or the right side, and then also from the other side, and then observe what your y values are doing. Right? If you can't make any sort of observation, you're like, I don't know what they're going to, then maybe maybe you can get closer, make it get sufficiently close. And if it looks like they're approaching some value, you can say, all right, looks like the limit is. Now, I would say things like the table here suggests that the limit is 1, right? Because this isn't a proof. It looks like it's getting close to 1, but how do I know it's not getting close to 1.000578, right? And the answer is I don't know. And that's really the limit, no pun intended, of using tables to do limits, right? There's a limiting constraint there. They can suggest what you think the value is, but they're not always 100%, especially when the functional value that you're dealing with, that you're approaching to, doesn't even exist. Like in this case, it doesn't even exist. All right, so that's us evaluating a limit numerically by making a table. Not the most exciting thing in the world, but again, it does bring us back to that whole like approximation procedure, right? Where we're getting closer and closer and closer. We will learn a way to prove for sure, for certain, directly, that the limit of sine x over x as x goes to 0 is 1. But we're not there just yet. So basically, I showed you how you can visualize it graphically, but at the same time, numerically, this is what's going on. All right. The next question that was on this sheet here, it's a little bit different, but not as exciting. But let's go ahead and do it. It's the same function, limit of sine x over x as x goes to 2, right? And we want to do this numerically. So what we would do now, right? Since I'm going to 2, maybe you can pause the video and see what you would do in this table. Where are you going to put that? Hopefully you say put it in the middle. So now I would put 2 here. And what I would want to do here is I would want to pick values that get close to 2 from the left side, right? And that values that get close to 2 from the right side, right? So, and there's no specific way you have to pick them. And, I don't know, I like to pick them so that they're symmetric, but you don't have to. So in other words, you can have like 1.999 here and then 2.001 here, and then just do one less 9 and one less 0 and kind of do about it that way. This one, like I said, is not as exciting because what do you know about at 2? The functional value actually exists. So that should be the limit. But I actually want you to do this on your own. It's something you should be able to do. Plug these values in and see as you're going this way and as you're going this way, are you getting a limiting value that's getting closer to what looks like around 0.4546? Right? Sometimes we do weird things when we think we're immediately to the left of 2, but we're really not because of the value we picked. That might happen to you, and you'll probably teach yourself something as you do it. Okay, but that's it. That's a wrap. Nice and quick. That's doing limits numerically by way of a table. Okay, be good.